Howdy, folks. We're continuing to talk about electric fields near continuous charge distributions. In this case, another charge stick of finite length L. And we want to find field strength distance x from the center of that rod. All right? And there are a couple ways to do this. And I'm going to show you a way that maybe is a little less common to do, but I find it a little more satisfying. All right? And so it's still, all these sorts of approaches are going to deal with the idea that there's a little piece of charge right there, dq, that creates a field at this location dE that looks like that. Now, important to note that there via symmetry is another little charge, an equal distance on the other side of this line that makes an equally sized dE that has an equal x component but an opposite y component. And therefore, when we are finding our net field, we're going to add up all the infinitesimally small dEx's, which is to say that the net field is the integral of all those dEx's, which is to say of all these dE cos thetas. Okay? Now, at this point, what you have is a couple of options. And one of the options, for sure we can go to the next sort of step where we say each dE is k dq over r squared. All right, and what we might do here, at some point you're going to have to deal with the fact that this stick has a charge density q over L, and so therefore a total charge of lambda L, and therefore an elemental charge, amount of charge, can be written as lambda dL, which we might call that a little dy, so it wouldn't be so rare to call that a dy. But so now we get that E is k lambda, so far constant, r squared, well, r changes, and cos theta, well, theta changes, and then we got dy. Did I capture everything? Lambda dy cos theta. Yeah, so we got two variables and d something else. Well, that's not good. Right? That's unsolvable as it is. So here's where you have a couple of options, and you can choose what you want to express in terms of what, and what you want to integrate, what you want to use as limits of integration and a variable to integrate by. All right, and a standard way to do it, this is an aside, but a standard way to do this is to do something like, let's pull out this k and lambda. I'm going to do this a little bit quickly, and you'd say something like, well, 1 over r squared. R is x squared plus y squared, right, where here's y. And then cos theta is x over r, x squared plus y squared to the 1/2 dy. Nice thing now is that x is a constant. We're saying at position x. And y is our variable. And then you have to integrate k lambda. You'd go from negative L over 2 to L over 2 of x, which is a constant, so you can pull it out if you want, but x squared plus y squared to the 3/2 dy. And lots of people will say, well, this is a standard integral. 1 over the 1 over x squared plus y squared to the 3/2, or x squared plus y squared to the negative 3/2. That's a standard integral. It can be, we can just take our word for it, and you can. There's nothing wrong with it other than the fact that if you held my feet to the fire, I wouldn't be able to tell you why or how it comes out to what it comes out to. So therefore, one path is just to accept what the integral of that function is and press forward. And the other path is to say, let's integrate d something else. All right, so that's what I'll do. And to do that, let's go back to the place where we had two different variables, d a third variable, and let's change our approach. Okay, and so, what we did here was we wrote r in terms of x and y, x being a constant and y being a variable. But what we can also do is say, well, since cos theta is x over r, then that means that r is x over cos theta, and therefore r squared is x squared over cos squared theta. Well, that gets us at least down to one variable if we plug that into here and we say integral of k lambda over r squared. Well, that's x squared cos squared. And I'm going to leave it as separately this cosine squared and that cosine squared. Notice the x squared divided by cosine squared turned into, we just flip them around because we're dividing by r. But now we still have dy. All right, we only have one variable in our integral, theta, but we're dy. And obviously that's not going to work. So what we can do is let's turn dy, or write dy in terms of d theta. All right, and the way to do that is to say that, let's see. Well, we can say that tan theta is y over x, right? Where, there's our y, here's our y, here's our x. Okay, and that means that, well, y is x tan theta, right? Constant variable that we want. That's good. And then we can say dy d theta is, if we differentiate both sides of this expression d theta, it's the integral, the derivative of x tan theta d theta. Right? Why am I doing that? Because once I do this derivative, right, then I can say, well, dy is that derivative, and I can move the d theta over here. And then I'll be able to write my dy in terms of stuff d theta. And that's good. Now, here's a little something where, now remember, x is a constant, so we can say dy d theta is x times d tan theta d theta. We're much closer to a place where a lot of people, whether or not you know y, can just say, well, I know what the derivative of tan theta d theta is, because, we just memorize those sorts of things. It's a little easier than memorizing, oh, what's the derivative of, or the integral of blah, 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 blah to the 3/2. No, who's memorizing that? Probably people that do a lot of electricity and magnetism stuff. But anyway, what I can do is prove what the derivative of tan theta d theta is if you're willing to listen to a little quotient rule discussion. So if we say d tan theta d theta, that's the same as saying d sine over cosine d theta, a definition of tangent. Maybe not the definition, but the equivalent to tangent. Now doing this derivative is a quotient rule thing. And, here's maybe some more take my word for it, but somebody told me once that the way you do a quotient rule thing is you do low d high minus high d low over low squared. You ever heard that for quotient rule? Something that has stuck with me. And what I mean by that is like the following. D of d sine theta d theta well, sine theta over cosine theta. Well, here's our low and high. So we say something like low, cos theta, d high, so d sine theta, d theta. Well, d sine theta, d theta is cos theta. Minus high, sine theta. D low, d cos theta, d theta is negative sine theta over low squared, cos squared theta. Okay, okay. Now check this out. In the top, we have cos squared theta minus negative sine squared theta. Now everybody knows that that's 1 over cos squared theta. Agreed? So what we can say now, why do we do that? Again, we're trying to do dy d theta. We can say that dy d theta is x times 1 over cosine squared theta. I'll stash all this for a later date. Yeah. Okay, now we got to start putting parts together. Oh, well, there's not a ton that we still need to do other than say, what's dy? Well, check this out. Let's take this and get it up here. There's dy. Well, there's dy d theta, which is to say that dy is x over cos squared theta d theta. And now for this dy, if we put in that, now we're variable, variable, d that variable. And life is getting better. Okay. Well, you know what? It's about time we pull out k and lambda, is it not? K lambda, because those are both constants. They don't need to be integrated. Okay. Integral of cos squared theta, cos theta over x squared dy, x over cos squared theta d theta. Okay. Goodbye, 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 goodbye. Yeah? All right, so this is getting pretty simple now. Now we say that E is k lambda over x. Pull that out. It's a constant. And all we have left is cos theta d theta. Oh man, life is great. Now, what are the limits of integration? Well, where you usually integrate dy from negative L over 2 to L over 2, now we'd have to say what those angles are. You know, so how do we best express those angles? Well, that's a kind of a different question. Well, let's just say for now that, you know, however we want to express them, there's a lower and an upper that are the same if we are, you know, on the midway, on the bisector of that stick. All right, so that means that E is k lambda over x times the integral of cosine theta d theta. Well, that is sine theta, right? Evaluated from negative theta to theta. I always have to check there's my, yeah, okay. So the integral, so to get to the integral of the sine, that's a negative. Sorry, I just had an integral moment. So yeah, that is, was there a negative in here or not? Nope, there's no negative in here because that is the right integral. Those get hard for me to remember going back and forth between integrating and differentiating. But the bottom line here is, if this is a stick of finite length, then our thetas are less than 90. All right, and because, well, it's like negative something to something, right? So here's a sine curve, yeah, from negative, well, here's negative 90 to 90, right? So the sine of, you know, equal angles, or angles of equal magnitude on the opposite sides of 0 degrees give you the same number, but just with opposite sign. All right. So this is really E is K lambda over X times, well, the sine of theta minus the sine of negative theta. Where theta is the same thing, that's K lambda over X times 2 sine theta. And look, the only, well, these are all constants. All right. The only thing that can change, you know, if X changes, and that means theta changes, but what this means is, I mean, the sine of theta is going to be a number, right? And it means that the farther away you go from this, this stick, the weaker the field gets, right? So as I sometimes do, I just had to take a moment away and think about what this means. And what it does mean is certainly the farther you get away from this stick of finite length, right? Here's our stick again. As we go out from, say, here to here, well, X gets bigger, which makes the field weaker. Sine theta, well, the angle here, let's take, you know, from, well, here's theta. It goes from that to that. The angle gets smaller. And if the angle gets smaller, then the sine gets smaller. So top gets smaller, bottom gets bigger, E gets weaker. Yeah, as the field, as we go away from this, this stick. All right, that's good. Now, the other thing to consider is, you know, what are the real limiting cases here? And the one thing is, if the stick is really long, which is sort of like saying if we're really close to the stick, but if the stick is really infinitely long, well, then these two angles both approach 90 degrees, right? So if we're way in here, you know, the one angle looks like that to the top, the other angle looks like that to the bottom, and those are like 90 degrees. So in that case, what we get is E is K lambda over X times 2. All right, and then what that says is a couple of things. One, it says that it's really an expression for if this is a stick of infinite length. Because no matter where you are along this x-axis, if the stick is of infinite length, then the angle to get to the top and the angle to get to the bottom are 90 degrees. And what you get is this expression, which is really cool because it says that there's just an inverse relationship between distance from the stick and field strength. All right? Now, think of a point charge. You know, with a point charge, what you get is, well, we can only draw this two-dimensionally. right? With a point charge, we get that radial field, but these lines spread out both in the dimension, the plane of this paper, and in the perpendicular dimension. So that sort of accounts for the fact that there's an x squared in the bottom, or r squared, but x squared for a point charge. But this is really like a top view. There's an eyeball looking down on the top of this stick. We're seeing the field. It looks like this. And the farther, since these are straight lines, the farther you go this way, the farther apart they get. And that's that inverse relationship with E and X. So that's pretty cool. Okay? Yeah, and then check this out. So this is for L equals infinity. All right, now, how about this? For still our finite length, for L equals L, okay, sure, but X approaches infinity, gets really big. You gotta do a little juggling here, but we get something like this. We say that K lambda X is getting really big. Well, here's a 2. Now sine theta, okay, if X gets really big, this angle gets really small. Ooh, small angle. Small angle approximation means that the sine of the angle and the tangent of the angle are pretty much the same thing. So sine theta is the same as tan theta, right? So here's E. Well, check this out. That's 2. Well, you know what? I'm going to leave it as K lambda 2y over x squared. Well, we're getting towards something real good when we say that, let's see, K will leave lambda q over L. 2y is L, right? This is stick of length L. This is y. And then x squared. And check this out. If we're really far away, that looks like a point charge. Oh, yeah. You dig? I dig. All right, so a different way than you'll see a bunch doesn't mean it's better. I like it because I don't have to just totally fudge any steps other than saying, hey, did you know this is the quotient rule? I did. But I don't have to just refer to a table for an integral. But is that any better, really, than referring to a mnemonic device for a rule of how to take a derivative? I don't know. But I like this way. All right? So that's a field. These are a couple of expressions, right? The general, the limit for an infinitely long stick, the limit for really far away from the finite stick. Okay? Okay. All right.